Analyzing noisy data from physical tests and transient FEA. This unique 4-module training bundle teaches you the necessary skills to work with noisy, frequency-rich data that occurs in a variety of mechanical engineering applications. With our training, you will learn to turn this mess into success. Noisy, frequency-rich data comes from many sources, including impact, explosive, and failure events, high-rate material testing, and testing utilizing multiple sensors, as well as cyclic testing with optical strain gauges, and more. Whether this data comes from physical testing or numerical simulations, all of these kinds of data sets are stored digitally. Unfortunately, many mechanical engineers have had little to no education on how to work with such data. They are not sure how to avoid distortions and errors, nor how to interpret results that are meaningful and accurate without a lot of doubt. To successfully collect, process, and interpret this type of data, you must understand many of these important topics that begins with sampling and aliasing and ends with a framework of proper workflows to analyze data with confidence. If you are working in any of these areas listed here, this training is for you and your team members. Are you concerned that you or your colleagues may be unknowingly aliasing data? Is your organization having difficulty correlating simulations and physical test results? Our training will clearly explain the issues and technologies related to properly handling frequency-rich, noisy data. The courses teach you DSP fundamentals in terms that relate to mechanical engineering, where we describe proven workflows, how to apply them, and to what problems. Each training course walks you through numerous examples to drive home key concepts. Modern test and simulation systems store data digitally via sampling of a signal. This action opens up the possibility of aliasing if the time increment is insufficient for the frequency content being captured. Aliasing easily causes confusion as demonstrated here, where a small change in the sampling frequency appears to make the signal flip upside down. It actually caused a 180 degrees phase shift. Aliasing misrepresents high-frequency components falsely as low-frequency components, and it can occur when taking physical test data or storing output from transient numerical simulations, such as explicit dynamics or other analysis codes. It can also occur when you decide to represent existing data with fewer number of points. Our training will teach you multiple approaches to avoid the nightmare of aliasing. Here's a typical impact study that shows why aliasing can spell disaster. In this example, the engineer is ultimately intending to evaluate up to only 5 kHz frequency content of the acceleration data. Improperly following a rule of thumb a colleague told them, they output the transient FEA acceleration data with a 50 kHz sample rate, thinking that was sufficient to represent up to 5 kHz content. The physical test data of the same event looks totally different from the simulation. After applying a 5 kHz low-pass filter to both datasets, the results are a disaster. No correlation whatsoever. Our training will teach you how to output the data from the simulation properly, avoiding aliasing, so that when you apply an appropriate low-pass filter, you can achieve amazing correlations between tests and simulations. Aliasing, like shown here, is the #1 problem for the simulation community. Unfortunately, aliasing can also appear in physical tests too. Consider this data acquisition product for collecting transient strain gauge measurements supplied by a major vendor in the test and measurement market. The product digitally captures analog signals, providing you with a nice ASCII file of your transient strain data. Except this hardware the vendor is selling has no anti-alias protection. It just blindly samples signals, and there is no warning of this danger anywhere in its product literature nor its manuals. Focusing on numerous examples from mechanical engineering and nonlinear mechanics, this course teaches you how to properly collect data avoiding aliasing, how to then interpret its frequency content with Fourier analysis and other tools, and then how to filter it with confidence. Unfortunately, not all DSP methods work equally well on all data. Here is some noisy force displacement data from an explicit FEA model. Filtering this with a single-pass Butterworth low-pass filter looks smooth until we compare it to the benchmark and see we have a 22% error. Using a bidirectional filter with an academic implementation seems to help in one portion of the curve, but looks terrible at the end of the data. and using an FFT filtering approach creates undesirable end effects. Training will teach you why these various filter distortions occur and strategies to avoid them, so that you can achieve robust and accurate results with a firm understanding of the DSP process. A common misunderstanding in shock data is that many people want to judge the shock severity by the peak acceleration recorded. Here are two highly transient, frequency-rich shock signals. Both have fairly similar peak acceleration values. This peak acceleration assessment does not tell you which environment is the most severe, but a pseudo-velocity shock spectrum analysis does. In this example, a PVSS assessment clearly shows that over a very broad range of payload natural frequencies, the X environment will clearly be worse than the Z environment. Analyzing shock data is an important topic in the general discussion of noisy data analysis, so much so that we have an entire training module dedicated to the topic. In this module, you will learn how to perform shock response analysis and the benefits of a PVSS analysis over more traditionally utilized absolute Excel shock response spectra. You will learn how to create and interpret PVSS plots like the one depicted here, including how to estimate effective G-loads, payload relative displacements, and dynamic energies experienced by payloads. This training also demonstrates how you can use a PVSS plot to quickly assess the plausibility of shock data from both physical tests and FEA. Our unique 4-module training bundle is taught live by me, Dr. Ted Deal, leveraging my over 30 years of nonlinear mechanics expertise. Comfortably attend these training sessions via Zoom from your home or office. Each of the 4 modules is a multi-session interactive course with ample hours of training and where your questions are encouraged. You can take all 4 modules at a discounted price or take whichever modules meet your needs. For more information, including detailed class outlines, and to register for upcoming classes, please visit our Bodhi Tech website. We look forward to seeing you in a class soon.